And information Matthew 14 linear algebra class. Let's go ahead and get this started. So what is interpolation? Interpolation is finding the function that exists between 2 points or more. For basic linear interpolation, you'll have 2 points to which you would try to find a function that passes directly through both of those points with a straight line. As we add more data points, we're able to introduce curvature to our line. The function we will find between these data points will pass exactly through each data point. Unlike regression, which would just pass through a set of data points closely, interpolation will exactly pass between the two of them. How can we find interpolation? Well, there's 2 main methods used today to find interpolation. First is using the Newton polynomial method. It uses a divide and difference method to where then you apply those answers into a polynomial method. This has a recursive divide and difference portion, and then as things are placed on the stack, the divide and difference is computed. Then when they are removed from the stack, those values are then used to build the polynomial equation. And then we have the Lagrange polynomial. The Lagrange polynomial is actually just a simplification of the Newton's method. It uses the same mathematics, it's just we're able to skip the step of the divide and difference and have a set of equations we can plug directly into. One of the benefits of, I'll get to that in just a second. Also, when finding it, there's only one polynomial that's going to perfectly fit it, and you have to have n plus 1 data points to find a polynomial of nth degree. So we need 5 data points to find a 4th degree polynomial, 2 data points to find a 1 degree polynomial, etc. Or in that case, a linear. The benefits of Newton's method is the divide and difference table, new data points can be added at any time, and these data points can just be used to create a higher order polynomial. We won't have to recalculate previous data points. They're still useful. If the data points are also equidistant from each other, this becomes significantly easier as a pattern emerges between in the divide and difference formula. A couple of applications of using this would be digital signal processing, where we want to do upsampling. This will help reduce noise reverberation due to the amplification, going to a higher sampling rate. Star and planet positioning is actually one reason why this was invented. Newton was having a difficulty plotting positions of stars and planets, and he used this formula to do that. We can also use this to find numerical differentiation, numerical integration, and solutions to differential equations. So this could be useful in larger problems where you need to find that. Linear interpolation is the most basic. It's where we have 2 data points and we want to draw a straight line between the 2. This is a basic equation for drawing a straight line between 2 points. And we can solve for f sub 1 of x to give us the equation. Now this will look very similar to our slope-intercept form, where this is our b, our x is here, and this is our m. And the slope is just the difference in the rise over run of the 2 points. Again, f sub 1 designates this as a first order interpolation polynomial, straight line, very basic. The next step is to get into an actual polynomial. Here you're going to have 3 or more data points to get a second order polynomial, and we can go up from there. Here's what a basic one would look like. Again, we're still at a straight line. We've got 2 data points. This is a first order polynomial. Now for a second order polynomial, we can see that we've basically taken what we've done here in the first one and applied that a second time to those 2 points again. This again shows how the function is somewhat recursive, and something that we specifically look for when developing software applications, recursive code that we can do over and over again. This is why the Newton's method and Lagrange polynomial are significantly different than what we may have been taught in class. These are used for recursive programming only, and this is something that we found on a group project. We're actually using Lagrange polynomials, so you'll get to learn about that when we do our group presentation, but today I wanted to focus on Newton's method so that you understood that before you moved into the more complex Lagrange polynomial, which this is based off of. So we'll start off with the most basic form. This is the basic form of a Newton's polynomial here. We can see here it chains together the first order, second order, third order, fourth order, nth order polynomials here. And these are the basic equations we use to build those. I'll break those down for you here. to find b sub 1, this is just the basic equation I showed you on the previous page. B sub 2, we're moving up, same thing here. B sub 3, B sub n, we're stepping up and we're just basically chaining this multiple times. Now what we use is a divided difference table to figure this out. So kind of here's what that would look like. Here we would have our x values, our y values for every x. We will start with those. You'll be given those when you're doing that. Here we have 4 data points, so we could come up with a third degree polynomial. And how we start to do that is, for our first set, we will add another column here. We will find, off of our previous slide, we use that equation here. We will use x sub 0 and f sub 1 to do that. We would do the same here. We would use 1 and 2. Here we'd use 3 and 2. So we're basically losing 1 degree for every time we do that. Again, we would do the same thing here, and so on and so on. And we can just step immediately into an example of that. I've copied the table over from the previous slide so that we can follow along with it, along with the basic 2 equations. So for example, to do f of x sub 1, x sub 0, we'd use this equation here, where we would use f of x sub I minus f of x sub j over x sub I minus x sub j to determine this here. So to start off the problem, I've given us a set of 4 data points, and you can see our x values here and our y values here. So let's go ahead and just compute this column here. What we would do is we would take the f of x sub I, which would be our 14, minus our 2 over 2 minus 0. So we would go ahead and get 6 there. We will just do the same thing all the way down. So we do it with the 60. We will use the x sub 1 and x sub 2 data points for 168, the x sub 2 and x sub 3 data points, and so on. From here, we could actually give you a linear equation based off of that, but we need to be more accurate. We have more data points. We'll go ahead and we'll step this out one step further. We'll add the next column on. This does these. It uses a. You want to use the values from the previous column in this column, so we can see the equation here. We have the f of x sub I sub x sub j. So we would take our 60 minus our 6. And then what we would do is we would start with our 3 minus 0 for the denominator. 60 minus 6 over 3 does give us 18, in fact. But again, we'll follow the same pattern here. What we're doing though is we're always referencing from where we are, say our x sub 2, all the way back up to x sub 0. We're not just going one step up for our denominator values. Again, we'll continue the same pattern out. For the 9, we would use 54 minus the 18 over the 4 minus 0. Very simple stuff there. Keep stepping through the values. We have reached as far as we can. We've got a 1. So here we would use the actual Newton polynomial. We've just done the divide and difference table. And so for example, for our first order linear value, we would have 2 plus 6, and then we would multiply 6 of the x minus 0 from our x value. Now if we want to go ahead and get a second order polynomial, we need a third data point. So we'd just tack on there. We still got our 2 plus our 6 times x minus 0 for that, plus 18. Now we would again do x minus 0, and then our next data point, x minus 2, and so on. For our third order, we would also continue the same thing, again adding on a plus 9, multiplied by the x minus 0, by x minus 2, by x minus 3. And again, we can get to a fourth order polynomial by using this same method. So by having more data points, we're able to get a significantly better polynomial. It's going to have more curvature. It's going to go through each and every data point. And for example, if we added another data point at a later date, we would just add that on here. We'd have an x sub 5. We could go out one step further with the whole pattern here, and we would be able to create a fifth order polynomial, and it would go through that point also. If there are any questions, please post them on the discussion board. I'll be happy to respond to them. Hopefully my sound issues were resolved this time, and thank you for your time.